Swayam Prabha. Digital India. Educated India.
Welcome back. In lecture 30, we continue with our data analysis and visualization. This is part 4 of those lecture series. Again, it looks into exploratory data analysis, of course. So in this lecture, we will talk about the SciPy functions a bit at the beginning, and then we'll move on to ANOVA and then to MANOVA, and finally we'll look into 2 non-parametric tests. One is Kruskal-Wallis and one is Manchester-Whitney U-test. Now, all these tests are required in the context of building machine learning models. So, before we build a model, sometimes we need to do we need to test the relationships and all these things, and sometimes there could be hypotheses of how things are related together. So, that is where this sort of analysis will come. Now, the SciPy function is more or less it's used for applied data analysis, and more or less it is extension of NumPy with more advanced numerical algorithms, both for optimization, statistics, signal processing, integration, scientific modeling, and so on. And you can see that all different types of things we can do with this. We can go for optimization, linear algebra, interpolation, signal processing. All these things can be done. And for example, some scientific and mathematical functions, special functions could be also called in, like SciPy special, then gamma, then ERF, all this. And then, for example, optimize.minimize, optimize.carve, fit. These are all optimization functions. What we do over here is we want to do fit a curve which is nonlinear, and we want to fit that curve, and we want to get the values of those coefficients and all, or those beta coefficients. So, this is what we can use. So, these are basically curve fitting exercises. And then there is linear algebra, where advanced linear algebra could be done, such as this linear algebra inverse, linear algebra solve, and so on. Then EIG. And then numerical integration could be done, interpolation could be done, interpolate.interpid, and then interpolate.grid data, and so on. Signal processing like filtering, convolution, and peak detection in time series data. All these things also could be done, like signal.find peaks, signal.convolve, signal.butter, and so on. So, these are the different types of functions. Again, not everything is required at every time. Whatever based on your analysis, sometimes we will call those, and then we will learn about those. And you can see over here, we can do first Fourier transforms. We can use sparse matrices. Over here, we can do sparse functions related with sparse matrix like CSR matrix or CSC matrix. Then all the distribution and all the test that if a particular variable belongs to something, we can check the distributions, and like chi-square test, Pearson, all these things could be also done here. We can do some amount of image processing, like image filtering, scaling, and so on. And then we can do clustering, like we can do hierarchical clustering, spatial clustering. So, spatial.kd tree, and this is a dendrogram, this is a hierarchical clustering. Then input and output utilities, those are there. So, more or less it is based on NumPy, and it is used in by stats model, SciPy, sklearn. So, these are the higher end libraries which are also going to utilize functions from this basic libraries as well. So, this is one of the these are one of the major libraries that are used in the different day-to-day machine learning activities. So, now what we have learned till now is we have learned to understand the relationship between variables, and we have also tested the relationship between the predictor variables, and then we have moved on to VIF to see if that is that is not contributing, or if the amount, because of this interrelationship between the predictors, what is the effect of each contribution if I want to determine that. So we have done VIF and all. So that actually help us to identify which of the features we will keep included in the model. So that's the purpose of that. Now ANOVA and MANOVA, both of these tests, and it tells us that whether categorical spatial groupings, for example, whenever like for example, all the gases NO2, SO2, CO2, because all these are related together. Now, can I say that all of them vary together in regards to area, like industrial, commercial, residential, and so on? So that is important. That means if the entire group is also being affected, right? So ANOVA and MANOVA tests whether categorical spatial groupings exert statistically significant effects on pollution level. And this helps in determining regression model specification, should the predictor be included in the model or so on. So for example, suppose we say that the effect on residential, commercial, all these things are exactly same. That is, there is no separate kind of effect. Then there is no point of including that into the model. But if I include that into the model, or rather what I can do is I can group the data into 3 groups: residential data, industrial, and then develop separate models out of that, right? So these decisions can be coming out from ANOVA and MANOVA test. So we are using the same data set as earlier. So we have got the air quality monitoring stations, the land use, and then there is traffic volume per day, industrial activity, density, and then the values of all the emissions for each of these gases that we are measuring. Now, the full form of ANOVA is analysis of variance. It tests whether means of continuous variable differ across multiple groups. So if I've got many groups of data, if the average values are, if I'm taking, if those are different from each other, and is it statistically different also? It is not like just looking at it saying it's just a little bit different, that its value is a little bit different, then it's not right. Why? Because sometimes what happens is, that means if the variation within the group is different from the variation among the different groups. So that is what we are trying to understand. So what we can do is we can use this to compare different urban zones such as residential, industrial, commercial, in order to identify differences in pollution levels, traffic intensity, or environmental conditions, and so on, right? So we do some assumptions, of course. There is independence amongst the observations. Not each one is not affected by the other. Approximate normality within the groups, and then homogeneity of variance across groups. That is, across the groups there is this variance is homogeneous. So we can start with the null hypothesis H0, that is the means of all groups are equal. That is, the average NO2 concentration, in this particular case we are working with NO2 concentration, is same in residential, commercial, and industrial zones. So what it means is we will take the residential zones, measure the NO2 from each of these zones, and then take an average of it, and then we go do for commercial and industrial, and then we see that if it is matching or not. And the alternative hypothesis H1 is at least one group mean is different from the others. So that means it is not the same. So how we do that? Of course, we don't measure the mean directly. What we do is we will measure the variance between the groups as well as variance within the group. So now ANOVA is measured with F equal to between group variance and divided by within group variance. Now between group variance is basically the effect of land use, whereas the within group variance is the natural variability amongst the data. Now once we do that, then we get the F ratio. When F is almost equal to 1, that is between group variance is almost equal to within group variance, we fail to reject the null hypothesis. That is, the mean of all groups are equal. So that is the case. Then F is greater than equal to 1, which is moderate. Signal is stronger than noise. Possible land use effect is there, but we need to check the p-value to see if it is significant or not. Then finally F is much greater than equal to 1. So that means the land use does play a role. That means That means each land use is different, right? So the p-value is the probability, now p-value is the significance value. It is the probability of observing an F statistic at least as large as the one computed assuming the null hypothesis is true. So what it does is we check that if the significance, if it is more than the 95%, we take 0.005, that is represents the 95% confidence interval. So we will reject the null hypothesis if p-value is lesser than this 0.005. But if p-value is greater than 0.005, we will be failing to reject the null hypothesis. So let's see an example over here. So we are doing this via Python code. We import pandas as PD from scipy.stats import f underscore one way. So that's the function from the scipy module, and then from the scipy library. Then we store the data in the df, the data frame, and then what we do is we will first split the data as per the land use. That means we take each of this residential, that means where within df if the area is equal to residential, then we are taking the NO2 values of that and then storing it in res. Similarly, we are taking for commercial, we are storing it in com, and then for industrial we are storing it in IND. Then what we are doing is we are calling one-way ANOVA function f underscore one-way, and we are giving the name of the groups for which we are trying to do this analysis, ANOVA analysis, between whom we are trying to find out if they are varying or not, and we are storing the two values, the F statistic and the significance value of this. So you can see over here, once I run this model, I print this, you can see F statistic value is given over here, and this is the p value. Now this actually is 10 to the power minus 5, so it is 0.0000146. So when this value is there, of course it is less than p 0.05, so we reject the null hypothesis because it is less than 0.05. So that means NO2 concentration differs significantly across the different land use types, and thus land use classification is a strong determinant of NO2 and can be included in the model as a predictor. Now ANOVA do not actually specify which specific groups differ or the direction of difference or the direction of this particular difference, right? Direction means is it increasing or decreasing and so on, right? So it does not specify that, okay, what is it just says it is different. It doesn't say what is different from what and so on. But to understand that, we have to do further test, and that is where Tukey's HSD test comes in. HSD is honestly significant difference. It is the minimum difference between two groups, means that it must be exceeded to declare them. That means it is the minimum difference between two groups, means that it must be exceeded, this value should be exceeded to declare them to be significantly different. Then we come to MANOVA, where we are what we are doing is we are doing a little bit different analysis. As we already have understood that pollution is not one dimensional, so we can have many gases which are together. So what we are trying to understand is if these are occurring together or are these are correlated. So that is what we are trying to find out. So in case of ANOVA, we have only considered one variable, whereas in case of MANOVA, we actually consider multiple variables, right? So what we do is it is used to test difference between groups when multiple independent variables are considered simultaneously. That means we will take all these variables and we will say, does this vary across the different land use, that is residential, commercial and so on. So all their values needs to be taken, right? Now, the question could be, does land use influence the overall pollution profile? So it is not only CO2 or NO2 anything, it is the entire thing that we are looking into. So the null hypothesis H0 in this case is mean pollution vector is the same across the different land use type, same as earlier, whereas in the alternative hypothesis it is at least one group differs in its multivariate mean vector. So, and when we do this, in this case there is no F statistics or significance is there, but we have got four new statistics. One is Wilks lambda, then there is Pillai stress, then there is Hotelling Lawley stress, and then there is Roy's largest root. Now, Wilks lambda is how much variance is not explained by group difference. That is what we are finding out. So, that means we are trying to measure how much is the variance which is not measured by the difference between the groups, right? So, which is beyond. So, if it is close to 1, we assume that groups are similar. If it is close to 0, we say groups differ strongly. But we also need to check the p-value associated with this. But if the p-value, even with all this, if the p-value is very small, we will reject the hypothesis, which is the null hypothesis, which is H0, and we will say that the mean pollution vector is not same across the land use groups. So, because if the p-value is less. Now, for pill-like stress, it is also a measure of explained multivariate variance. If the statistic results in value which is close to 0, then we assume that there is little group effect, but if the value is a large value, much more than 0, then we say that strong multivariate group effect does exist. And then for this Hotelling Lawley trace and Roy's largest root, we measure the significance of those significance values, and they actually is this significance of signal to noise ratio in this multivariate space, or this largest group separation significance of that. If both the significance satisfy that 95% confidence interval rule, we will accept. So, now running the program in Python, we first import pandas as PD, import stats model API as SM, and then we import this multivariate MANOVA from and import MANOVA from the stats model library. We first stored the data in the DF data frame, and then what we do is we are now storing the variables which would be used in the formula for calculating. We are putting the features which would be going into the MANOVA function. Now, NO2, SO2, CO2, CO is being considered together, and ozone is considered together as the group of variables. And this is on the left side, we put this multiple dependent variables, the joint pollution profile in this particular side. And on the right side, we have the grouping factor, that is on what basis we will group them. So, this is over here, it is the area, that is based on land use, we are grouping them. So, we are measuring that across these different groups, are this pollution profile or are the profile of this group is varying quite significantly, or it is just noise, right? So, once I run the model, it prints the statistics manova.mv underscore test function. So, you see this, the first set of values are for the intercept, and the second set of values is for the actual area for this particular feature that we have put in. So, there is beta 0 and then there is beta 1. So, beta 0 is the intercept and beta 1 x1 is the actual variable, and so we would be more concerned with this particular values. So, that means Wilks lambda we are finding for the the first for this particular area feature which we are testing here. So, the first one is 0.0012, which is extremely close to 0, and so then that means that land use groups are highly separable. Then there is pill-like stress, which is 1.865 with p value of 0.0001, which is strong and also statistically a significant multivariate effect, which we also established earlier. Then for Hotelling Lawley's and Roy, these two estimates, we get significance values are much lower than 0.005, and then we can accept this. That means the fact that we can reject the null hypothesis, and we can say that land use categories have significantly different joint pollution profiles. Next, we will look into non-parametric test, and the first one we will go for is the Kruskal-Wallis test. And here what we are looking into is are NO2 levels statistically different across land use types, but we are not assuming normality. So, that is the difference, right. So, Kruskal test is it's for cases where either the sample size is small, there are a lot of outliers, there is non-normality concerns. So, that is the biggest thing, and then there is mixed measurement precision of the different variables, and it's a alternative to ANOVA. So, more or less we are trying to do the exact same thing what we have done with ANOVA earlier. So instead of, because these values are, we are not concerned about the actual values, so we take the ranks in this case, and this test compares median ranks and not the means, and these are also distribution free. So that means there is no assumption of normality and there is no assumption of mean and all these things. So this tests whether multiple independent groups come from the same distribution. So that is more or less what we are testing. So the hypothesis could be written like the null hypothesis: distributions are identical across groups. That is, there is no difference in the central tendency. And the other one is the so here it is central tendency instead of mean, right? Median values, or here we are going to use rank values. And then the alternative hypothesis is at least one group differs. So first, how do we do that? First, we combine the observations from all groups, and then these observations are ranked in, based on their values 1, 2, 3, 4. We will give the ranks. Now, average ranks across groups. Then what we do is we will, once we have done that, then for each of these groups, whatever is the average coming, that would be compared. So if groups have similar distributions, that is, average ranks are similar, and if one group has higher values, then it is given the higher average rank. So Kruskal-Wallis test statistic measures how far group rank means are from the overall rank mean, and small h, when the value of h is small, then basically the groups overlap strongly, and for value, when the value is large, then the groups actually, we can say, it differs substantially. And we also have p-value to check if this difference is statistically significant as well. So this test does not tell us which groups differ, neither can measure effect size also. And so for that we need further test where we go for pairwise test, and for that we have got another test as well. So in this particular slide, we are going to demonstrate the program for Kruskal-Wallis. So we import pandas as PD from scipy.stats library. We are importing Kruskal-Wallis as well as Manchester-Whitney U-test, which we will do after this. And we are reading the CSV file into the data frame, and then what we are doing is we are first trying to extracting the NO2 values for each land use group, and also we are making sure that we would be not accepting empty values and all. And then you can see over here, that means for residential we are taking the this NO2 value and then calculating median out of that. And once it is done, then we can also print the group sizes and all these things, like print group sizes, residential length for res, length of com, and length of end. It just tells us how many variables are there. And then we can also print the group medians also. For each of these groups, we can also print the median values, as we are saying. So here you can see that residential 4 observations are there, for industrial 3, and then the median values you can see, like for residential, commercial, and industrial, we are getting the median values. And so then what we are doing is we are here we are actually calling the Kruskal-Wallis test for all these 3 categories: residential, commercial, industrial, and we are storing the age value and the p value, which is the age statistic, and the significance value, which is p statistic or the p value. And so over here, what we are doing it, once we are running, we are printing that Kruskal-Wallis test result. We are printing the value of age statistics and the p value, and then we are just doing a basic if and else decision. That is, if p value is lesser than 0.05, which is alpha, then we will print that the decision is to reject the null hypothesis, and at least one land use group differs in NO2. Else we will print that it fails to reject the null hypothesis. That means no evidence of group difference. So over here, drop NA, as I was telling you, it removes any missing values, and we can then once we have done that, then we are calculating the median of it, and then we are running the Kruskal-Wallis function. So here you can see the age statistic. It is coming as 8. P value is 0.01, which is significant. So we can decide that we can reject the null hypothesis, and that means there is at least one land use group differs in NO2. Now beyond the Kruskal-Wallis test, we also require further tests to understand, that means which group should differ. That means amongst the different groups, which are the groups which are differing. The previous test just says that there is difference. So over here what we do is we do pairwise test to determine which of the, where there is the difference, where is the difference originating from. So the Manchester-Whitney U-test is a non-parametrical statistical test used to compare two independent groups to determine whether one group tends to have larger or smaller values than the other. So again, if the sample size is small, the distribution is skewed, there are outliers, normality assumptions are violated, then only we will go for this Manchester-Whitney U-test. So in this case, we compared the ranks. In the previous one, we compared the medians. So here we were comparing the ranks of observations rather than the raw values, and also we assume there is no normality as well. So null hypothesis H0 is the two groups have identical distributions, and alternative hypothesis is one group tends to have larger values than the other, and the U statistics counts how often a value from one group exceed a value from the other. Now what we do is, that means we have first list all the things, that means values from both groups are first pulled together and all values are ranked, and then ranks for each groups are added separately for each of these groups. So that means when we are listing them, all the values of the variables, then after that we give the ranks 1, 2, 3 for each of these variables as per that order. But then I group the ranks for each of these groups separately. So you see over here R1 and R2 are the sum of ranks for the two groups, and then N1 and N2 are the sample size. So over here you can see, from here you can calculate the U1 and the U2 value for the for these two different groups for these ranks, and then we take the minimum of that particular value, and that value is nothing but the U statistic. And what happens is, if that value is small, then there is strong separation. If the value is large, then there is overlap. So over here, what we are doing, we are actually implementing this Manchester-Whitney U-test. So before we do that, you have to know one thing. Because if we are trying to do many Manchester-Whitney tests together, there may be type 1 error, that is, we are incorrectly rejecting a true null hypothesis, and that chance of that increases. So we do a correction which is also known as Bonferroni correction. So what we do is we measure the adjusted value of alpha, where alpha is divided by the number of comparisons. That means whatever is the significance variable that we will get for this particular test, we will divide it by the number of comparisons, and then that would be the actual value which we have to check if the value is significant or not. So in case of 3 pairwise test, rescom, resend and comment, we have to adjust 0.05 divided by 3, which comes to 0.10167. So that means if the p values are lesser than this, then only we will consider the result as significant. So first we in this part, the program, of course the import part, all these things remain the same we continue. So we decide this, we create a list of tuple, and this contains the name of the first group, the name of the second group, and the data values for the first group and the data values for the second group, or this series. So so this is what we are doing: residential, commercial, res, com. So these are the data values and these are the names, right? So we have done it for all the different pairs, and we have stored them in a tuple. Now what we are doing is we are doing the Bonferroni correction. So we take the alpha value divided by the length of the number of groups. So obviously in this case is 3. So we get that value. We can print that, and as you can see, it is printed. Bonferroni correction is 0.0167. And then what we are doing is we are printing the n post hoc pairwise Manchester-Whitney U-test Bonferroni corrected alpha, and what we are doing is we are printing this particular f string value of alpha, that correction value, and that is what is getting printed over here. And then for each G1, G2, A and B in pairs, because each of these are given in pairs, we are running the test, and then we are saying the Manchester-Whitney test is being run and A and B is being passed over here. These values are being passed, and then it's a two-sided test. That is, what we do is it tests for any difference. It is either higher or lower in between these two groups. Both are tested, and once it is done, then what we get is the significance value, which is stored in sig, and this value we can again check that if it is lesser than alpha corrected, that Bonferini collection, then it is not significant. We can print that, otherwise we can print it is significant. So that is happening over here, residential versus industrial. This is the U value and this is the P value which we have got. So it is not significant. Similarly, we can find for residential commercial and commercial industrial. So this is what has got printed, and because it is it's in for loop is there, so it is printing one at a time for each of these pairs, and that got printed, and we can test if the Manchester-Whitney test, if we can reject that. In this case, if there is we can form the hypothesis, and if we can reject it or not, we can test. So these are some of the references we have used. And to conclude, ANOVA, MANOVA and non-parametric tests provide formal statistical evidence of group level differences. They complement correlation and regression by validating whether categorical groups meaningfully shape outcomes. Thank you.